Quantum computing. Imagine a technology that could allow hackers to access everybody's passwords worldwide in a matter of minutes, or with the right adjustments could create unbreakable encryption and information security. These are just a few potential consequences of breakthroughs in the field of quantum computing, which applies the unique laws of quantum mechanics to developing computers with remarkable capabilities. The development of quantum computing is widely considered to be the next major leap in humanity's technological advancements, and when mastered is expected to give way to a new era of near unlimited possibilities, including both terrifyingly dangerous repercussions, which include the destruction of cryptocurrency, cryptography, security, and more. Yet, it also entails incredibly inconceivable benefits for humanity, from solving complex equations hundreds of millions times faster than the computers we have today, to helping to research treatments for illnesses such as cancer and Alzheimer's disease. But preceding all of this, how are quantum computers different from the computers we use today? The computers we use today are known as classical computers and use binary code to function. This means that they process data made up entirely of ones and zeros, and as most people know, computers can only understand these two values, which can be seen as on or off. Imagine a light switch. It is always either on or off, there is no in between. There are only two possible states. This means that it takes a lot of ones and zeros to display information. For instance, the singular letter A in binary can be represented as 011000001. Spelling out the word computing in binary would look like this. It might seem terribly inefficient, but that's because it is. Sure, computers process information with such speed nowadays, but they are far from perfect. This is when quantum computing comes in. Firstly, what is quantum computing? Not sure what quantum computing is? Don't worry, you're not alone. In very simple terms, quantum computers are unimaginably fast computers capable of solving seemingly unsolvable problems. If you think your smartphone makes computers from the 1980s seem painfully old-fashioned, quantum computers will make our current state-of-the-art technology look like something out of the Stone Age. That's how big of a leap quantum computing represents. A quick Google search will show you that a quantum computer is one in which makes use of the quantum states of subatomic particles to store information. But what exactly does this mean? Well, explaining it in simple terms is quite difficult because it's quite a complicated concept. Quantum means subatomic, and in computing, as in physics, is used to describe properties demonstrated by matter when we study them at a subatomic level. Often these properties don't seem to fit with the basic rules of physics that are observable when studying matter of atom-sized or larger. At the subatomic level, properties such as entanglement, a connection between particles that means they share the same state no matter how far apart they are, and superposition, where particles can behave as if they simultaneously exist in two different states, can be observed. One very important concept to understand is the difference between bits and qubits. As we know, classical computers store and read data in the form of binary bits that can either have a state of 1 or 0. Quantum computers instead use qubits, which thanks to the marvels of quantum mechanics, aren't limited to being simply either on or off. They could be both at the same time, or even exist somewhere in between. That's because quantum computing harnesses the particular phenomena that take place at a subatomic level. In particular, the ability of quantum particles to exist in multiple states at the same time, known as superposition, and this, matched with entanglement, which is the physical phenomenon that when two particles, such as a pair of photons or electrons, become entangled, they remain connected even when separated by vast distances, meaning they can be used to perform certain complex forms of calculation far more quickly than could ever be possible using classical computation algorithms. To help illustrate quantum computing, consider the following from Business Insider. Imagine you only have 5 minutes to find an X written on a page of a book in a library of 50 million books. It would be impossible. But if you were in 50 million parallel realities, and in each reality you could look through the pages of a different book, in one of those realities you would find the X. In this scenario, a regular computer is you running around like a crazy person trying to look through as many books as possible in 5 minutes. A quantum computer is you split into 50 million yous, casually flipping through one book in each reality to find the X. Many physicists from Albert Einstein to Carl Sagan have all agreed that the principles of quantum physics are so strange that they defy understanding. However, it is precisely these strange properties which are being harnessed to develop the next generation of computing. With all the technological advancements being made in this field, it is no surprise to many that quantum technology is soon approaching the mainstream. Goldman Sachs recently announced that they could introduce quantum algorithms to price their financial instruments in as soon as 5 years. Honeywell anticipates that quantum will form a $1 trillion industry in the decades ahead. But why are firms like Goldman taking this leap? A particular problem classical computers struggle with is a category of calculation called combinatorics. These calculations involve finding an arrangement of items that optimizes some goal, and as the number of items grow, the number of possible arrangements grows exponentially. And to find the best arrangement, today's digital computers basically have to iterate through each permutation to find the outcome and then identify which does best in achieving the goal. In many cases, this can require an enormous number of calculations. Think about breaking passwords for an example. The challenge of combinatoric calculations, as we'll see in a minute, applies to many important fields, from finance to pharmaceuticals, and it is also a critical bottleneck in the evolution of AI, which is just one more reason why the development of quantum computing is so essential. The somewhat incredulous risk quantum computers pose is how easily they can crack passwords, breaking every form of cryptography we know today, and going back to the cryptography work that Alan Turing did himself. But Shor's algorithm is a quantum computing algorithm which can be used to attack many current systems we use today. However, what many sensationalist, fear-inducing articles fail to mention is that we already have quantum-resistant algorithms. For example, the McEliece cryptosystem, which is resistant to Shor's algorithm. However, it is true that quantum computing could technically break even the hardest of passwords, as Google's quantum computer completed a calculation in 200 seconds that Google claimed would have taken the most powerful super classical computer 10,000 years to complete. Moore's law has long said that computing power doubles every 2 years, and since it was poised, it has been more or less true. But now Nevin's law suggests that computing power will start growing at a doubly exponential rate. Under Moore's law, computing power over 10 2-year periods would increase from 1 to 1024. But Nevin's law is doubly exponential and says that increase over 10 years would be 2 to the 1024th power, a number so large that it's hard to even comprehend. But don't worry about this happening anytime soon. Sure, quantum computers are working in labs and research centres already, but we're probably a long way from them becoming common. The real worry is for national security, since nation states may have these computers already and use them to try to crack encryption of other countries or of dissidents. But they may want to use them on their own citizens, so using the strongest possible password is still the best approach users can take for now. And as for the future of passwords, new techniques will have to be developed, extending the use of multi-factor authentication using more advanced biometrics such as Touch ID and Face ID and other techniques. Perhaps quantum computing will lead to the demise of the password altogether. However, what we must remember is that quantum computers will eventually break much of today's encryption, and that includes the signing algorithm of Bitcoin and other cryptocurrencies. Approximately 1/4 of the Bitcoin in circulation in 2022, valued at around $168 billion, is vulnerable to quantum attack, according to a study by Daylight. This shows that quantum computing is not only a dangerous tool for hacking, but also an incredibly lucrative business. Because even with a large enough quantum computer, you would still have to reveal or find somebody's public keys so they could be subject to a cryptocurrency attack. And with cryptocurrency wallet reuse being frowned upon, and a general encouragement of good privacy practices, the likelihood of this attack is already being reduced. Another area of attack could be Grover's algorithm, which can exponentially speed up mining with a large enough quantum computer. Though it's possible that ASICs, the specialized classical computers mostly used to mine Bitcoin now, would be faster compared to the earliest versions of more complete quantum computers. This poses a much stronger threat when it comes to the state of cryptocurrencies. The ability to mine quickly in a sudden quantum speedup could lead to the destabilization of prices and, more importantly, control of the chain itself. An unexpected quantum speedup could, if hidden, lead to a vast centralization of mining. It's conceivable that these avenues of attack and perhaps other, more unpredictable ones might emerge. Yet post-quantum encryption planning is already in progress, and through the mechanism of forks, a change to the Bitcoin protocol that restricts the rule set enforced by full nodes that update to enforce the new fork rules, cryptocurrencies can be updated to use post-quantum encryption standards and defend against these weaknesses. Make sure to take a look at my last video, A Cultural Phenomenon, Dark Patterns, and again, thank you so much for watching. Goodbye.